a lot of times you'll want to compare one function to another function. That might be to decide what investment to choose, or if you're a scientist, to see which population is growing larger, or if you're an athlete, to see who is going to win a race. And sometimes you'll be comparing functions when they are different types, like linear versus exponential. And a lot of times you'll have a function that is an equation and you need to compare it to another function that's in graph form or in a table. And you'll compare a whole bunch of different types of things. Maybe the starting value, which is the same as the y-intercept, or the rate of change, or maybe the maximum or minimum value of the function. And you might do that on an interval, meaning just for certain values of x. So all sorts of comparisons can be made between functions. Let's just do a couple of examples here. Let's compare these two functions. One is shown in a graph, and it looks like it's a linear function. The other one's in a table, and we don't know yet if it's linear or exponential or something else. Let's first try to figure out that. So let's see. 0, -5, 1, -3, 2, -1. It looks like each time x goes up 1, the function goes up 2. So there's a constant rate of change, a common difference, like in an arithmetic sequence. So this is a linear function also. And we could compare various different things. Let's first look at the starting value. Which one of these things, or I should say the y-intercept, because both of these might go on both sides of the y-axis. Which one has the greater y-intercept? Well, here on the graph, you can see the y-intercept is 0, -3. So at 0, the value of this function is -3. Over here, the value at 0 is -5. So the graph function has the greater y-intercept. How about the rate of change? Well, we already said that the table is going up 2 each time x goes up, so this has a positive rate of change. But the line in the graph has a negative slope, so it has a negative rate of change. So the function here in the table has the greater rate of change. And we could ask ourselves, for instance, on the interval 0 to 1, so when x equals 0 to x equals 1, which function has the greater maximum value? So let's see. For this function, the maximum value between 0 and 1 is -3, because that's a larger value than -5. So -3 is this maximum between 0 and 1. And over here, the maximum value between 0 and 1 for this is also -3. You can see the greatest y value there, or f of x value there, is -3. So they actually have the same maximum on the interval of 0 to 1. Now let's look at another example. Now let's take a look at these two functions. One is in equation form, and the other one is a graph. Now we should recognize this form here as mx plus b form, so it's a linear function. And we can see that this function here in the graph is not a straight line, so it's not a linear function. But we can still compare them. For instance, what is the y-intercept of each function? Well, we know in a linear function, the y-intercept is b in mx plus b. So here the value at where x equals 0 is going to be 18. And in the graphed function, we have y equals 20 when x equals 0. So the graphed function here, the exponential function, has the greater y-intercept. It's a little bit hard to compare rates of change between a linear function and an exponential function unless we specify a specific interval and we say the average rate of change. So I'm going to skip that for right now. But you could also look at maximum values on different intervals between the linear function and the exponential function. There's lots of different ways that you could compare these two functions, even though one is linear and one is exponential.